Hey everyone, and welcome back to the Deep Dive. If you're here, you know you're all about leveling up your knowledge game, and today we're tackling something pretty interesting. It's called linear programming. Yeah, I know it might sound a little intimidating, like something straight out of like a hardcore math textbook, but stick with us. It's actually way more useful and practical than you might think.
It really is.
It's all about finding like the absolute best solution when you've got all these different limitations. You know what I mean?
Yeah.
Like those classic dilemmas we all face.
Oh, for sure.
So to guide us through this deep dive, we've got some super clear explanations from a mathematics textbook. And our mission today is pretty simple. Demystify linear programming, see how it works in real-life situations that we can all relate to, and get a handle on those key steps to finding those optimal solutions. But don't worry, we'll do it all without drowning you in a sea of like crazy math jargon. Sound good?
Sounds good to me.
All right, so let's jump right in.
Yeah.
When we talk about optimization problems, like what are we really trying to achieve here? What's the big idea?
Well, at its heart, an optimization problem is all about finding the most efficient way to reach a goal. It could mean maximizing something we want, like profit or efficiency, or it could be about minimizing something we don't want, like cost or waste. You know what I mean? And linear programming is a specific type of optimization that deals with situations where the relationships between all those factors are well linear. They scale in a straightforward way,
That makes sense.
which makes it super useful in a bunch of different fields. I mean, think about how factories plan their production or how businesses manage their money and resources. It's all about optimization.
So it's kind of like finding that sweet spot where everything just clicks into place.
Exactly.
Okay, cool. Now, the textbook we're looking at actually gives us a great example about a furniture dealer. You want to walk us through that scenario?
Yeah, for sure. So this furniture deal, he's got a budget of Rs 50,000 to spend on furniture and a storage space that can hold a max of 60 pieces. So he's got these two constraints right off the bat. Tables cost him Rs 2,500 each, and he makes a profit of Rs 250 on each one. Chairs, on the other hand, are cheaper at Rs 500 each, with a profit of Rs 75. Now, the dealer's big question is what's the perfect mix of tables and chairs to buy to maximize his profit, assuming, of course, that he can sell everything.
Okay, I'm already starting to see the dilemma here.
Yeah.
Like if he went all in on tables, he could get 20 of them with his 50 grand, and that would give him a profit of Rs 5,000. But if he only bought chairs, he could technically afford 100.
Right.
But then his storage space limits him to just 60, which would mean a profit of Rs 4,500. So it's not immediately clear, whether to go for all tables or all chairs or some kind of magical combination in between.
Yeah, it's not that simple, is it?
No, it's definitely not. And this is exactly where linear programming comes in to save the day. It gives us a systematic way to tackle this kind of problem. But before we can even use it, we got to translate this real-world situation into, math terms.
Right. We need that mathematical formulation.
Exactly. So what are the key ingredients we need to put this furniture puzzle into that mathematical language?
Right. So first up, we got to figure out what are called the decision variables. These are the things the dealer has control over. In this case, it's the number of tables and the number of chairs he chooses to buy.
Right.
Right. So let's keep it simple. We'll use X for the number of tables and Y for the chairs.
Easy peasy.
Now, obviously, he can't buy a negative number of tables or chairs. That wouldn't make any sense.
Yeah, that's true.
So we get our first set of conditions. X has got to be greater than or equal to 0, and Y has got to be greater than or equal to 0.
Makes sense.
These are called non-negative constraints.
Oh, okay.
They seem pretty basic, but they're super important for making sure our solutions are actually realistic.
Yeah.
We're not dealing with imaginary furniture.
Right. Got to keep it real.
Hmm.
No negative furniture allowed.
No.
So what other limitations do we need to express mathematically?
Well, next up, we got to account for the dealer's budget.
Mm-hmm.
His total investment can't go over Rs 50,000. So if each table costs Rs 2,500 and each chair is Rs 500, the total cost has to stay under that limit. Mathematically, we can write that as 2,500 times the number of tables, X, plus 500 times the number of chairs, Y, has got to be less than or equal to 50,000. We can simplify that a bit by dividing everything by 500, and we get 5x plus y is less than or equal to 100. That's our investment constraint, all nice and neat.
Okay, so every combo of tables and chairs has to stay within that budget zone.
Yeah.
What about the storage space situation?
Right, that's another big constraint. He can only fit 60 pieces in total.
Uh-huh.
So the total number of furniture pieces, which is just the number of tables, x, plus the number of chairs, y, can't be more than 60.
Okay.
And then the last piece of the puzzle is defining what the dealer is actually aiming for, his goal.
Right.
And then the last piece of the puzzle is defining what the dealer is actually aiming for, his goal.
Right.
In linear programming lingo, we call this the objective function. And in this case, he wants to maximize his profit, make that money right. We can represent that profit as Z.
Okay.
And since he makes RS 250 profit per table and RS 75 per share, our objective function becomes Z equals 250x plus 75y. This is the equation we want to make as big as possible.
Awesome. So we've basically translated this whole furniture dilemma into a set of mathematical rules. Maximize Z equals 250x plus 75y, keeping in mind those constraints. 5x plus y less than or equal to 100x plus y less than or equal to 60x greater than or equal to 0 and y greater than or equal to 0. I feel like we've cracked the code here.
We're getting there.
But let's zoom in on some of these terms for a sec.
Yeah.
We've been throwing around objective function and constraints like it's nobody's business.
Yeah.
Can you give us a formal definition for each of those just so we're all on the same page?
Yeah, absolutely. So the objective function, it's basically a mathematical expression. And in linear programming, it's always going to be linear.
Okay.
It represents what we're trying to optimize, whether we're maximizing it or minimizing it. Like profit in our furniture example, it's always defined using those decision variables, which are the things we can actually control, like the x and y in our case. Right.
Constraints, on the other hand, are those linear inequalities or equalities that set the boundaries for our decision variables. They're the limitations we got to work within, like the budget and the storage space in our example. And of course, we can't forget those non-negative restrictions, which just mean our decision variables can't be negative. No negative furniture allowed.
Makes perfect sense. So basically, all these constraints together define what's even possible for the dealer, right? What do we call that whole set of all the possible combinations of tables and chairs that actually work within all those rules?
We call that the feasible region. Think of it as the playing field for all the valid solutions. It's the area on a graph that satisfies all those constraint inequalities at the same time, including those non-negative restrictions. Any point inside or on the edge of this region represents a feasible solution, a plan the dealer can actually pull off. Anything outside is a no-go. It's infeasible because it breaks at least one of the rules.
Got it. So we're looking for the best solution within that feasible region, right? What makes a particular solution the optimal one? The winner. Okay, so the optimal solution is the one that gives us the absolute best value for our objective function. If we're going for max profit, it's the point in that feasible region that gives us the highest value for Z.
Okay.
If we were trying to minimize cost, it would be the point with the lowest value.
Cool. So we've successfully translated a real-life problem into this math problem. We've got all our key terms down pat. But how do we actually find that optimal solution? The textbook mentions something called the graphical method. What's that all about?
Ah, the graphical method. It's a super visual way to not only find the solution, but also to really understand what's going on, especially for problems with just two decision variables, like our furniture example.
Okay.
It involves plotting all those constraint inequalities as lines on a graph. And then the feasible region is that area where all the regions that satisfy each inequality overlap.
So in our case, we draw lines for 5x plus y equals 100 and x plus y equals 60. And of course, the x and y axis for x greater than or equal to 0 and y greater than or equal to 0. Then we shade in the areas that fit the less than or equal to conditions and that overlapping shaded area that's our feasible region. All the possible table and chair combos the dealer can go for.
Exactly. And now here's where things get really cool. We can use something called the corner point method.
Corner point method. I like the sound of that.
It basically gives us a shortcut to finding that optimal solution by zeroing in on the corners or the vertices of that feasible region.
So we don't have to check every single point in the feasible region.
Nope. This method is based on two very important mathematical theorems.
Okay, I'm all ears. What do these theorems tell us about where to find that golden solution?
All right, so theorem number one says that if a linear programming problem has an optimal value, meaning there's a max or a min, and if the feasible region is a convex polygon, which it always is in linear programming, then that optimal value has got to be at one of the corner points, those vertices of the feasible region.
Gotcha.
Theorem 2 takes it a step further. It says that if the feasible region is also bounded, meaning it's totally enclosed and doesn't go on forever in any direction, then the objective function is guaranteed to have both a maximum and a minimum value, and both of those are going to be found at those corner points.
So instead of checking every single point in a potentially infinite space, we just have to look at a finite number of corners. That's a huge time saver.
It is.
But you mentioned something about unbounded regions. What happens then? What's the catch?
That's a great question. So if the feasible region is unbounded, meaning it goes off to infinity in some direction, then we might still find an optimal value at a corner point if it exists, but we're not guaranteed to have both a max and a min. We got to be a bit more careful in those cases to see if an optimum actually exists.
So it's not a foolproof method for unbounded regions. We might find a corner point with the best value, but it might not actually be the best overall.
Exactly. We have to do some extra checks.
Got it. So let's walk through the corner point method step by step. How do we actually use it?
Okay, so step one is to define that feasible region by graphing all those constraint inequalities and finding that area of overlap. Once you've got that, you got to find the coordinates of all those corner points, those vertices of the feasible region. You might be able to just read them off the graph if it's accurate enough.
Yeah.
But to be super precise, you got to solve the system of two linear equations that intersect at each corner point. Once you've got the coordinates of all your corner points, step two is to plug those x and y values into your objective function and calculate the value of z at each corner. If you've got a bounded feasible region, the biggest z value you get, that's your maximum value for the objective function, and the smallest z value, that's your minimum. The corresponding x and y coordinates, those are your optimal solutions.
Okay, that sounds pretty straightforward for those bounded regions. What about the unbounded ones? What extra steps do we need there?
All right, so for unbounded regions, after you find the biggest and smallest values of z at the corner points, let's call them m for the biggest and m for the smallest, you got to do an extra check to see if those are truly the global maximum or minimum. To check if m is really the max, you consider the inequality x plus by is greater than m, assuming your objective function is z equals x plus by and you're trying to maximize.
Okay.
If there are no points within the feasible region that satisfy that inequality, then m is your true maximum. But if there are points that do satisfy it, then the objective function can just keep getting bigger and bigger, and there is no maximum value.
I see.
And the same logic applies for finding the minimum. You check the inequality x plus by is less than m. If no points in the feasible region satisfy that, then m is your global minimum.
Okay.
But if they do, then no minimum value exists.
So we got to make sure that in an infinitely large feasible region, our best corner point isn't just a local champion that can be beaten by some other point way out there.
Exactly.
Awesome. Now, the textbook has some great examples to illustrate this method, right? Can we take a look at example one?
Yeah, absolutely. So in example one, the goal is to maximize z equals 4x plus y with the constraints x plus y is less than or equal to 50, 3x plus y is less than or equal to 90, and the usual non-negative conditions. When you graph those constraints, you get a nice bounded feasible region with 4 corner points, 0, 0, 30, 0, 20, 30, and 0, 50.
Okay.
Plugging those coordinates into the objective function gives you z values of 0, 120, 110, and 50, respectively.
Got it.
So the maximum value of z is 120, and it happens when x is 30 and y is 0.
Makes sense. And example two shows us how to find a minimum value, right?
Yep. This time we want to minimize z equals 200x plus 500y with these constraints. X plus 2y is greater than or equal to 10, 3x plus 4y is less than or equal to 24, and the non-negative constraints. The feasible region here is a bounded triangle with corners at 0, 5, 4, 3, and 0, 6.
Okay.
When you evaluate z at those points, you get 2,500, 2,300, and 3,000. So the minimum value of z is 2,300, which happens when x is 4 and y is 3.
Cool. Now, example three brings up something pretty interesting.
Yeah.
The idea of having multiple optimal solutions. How does that look visually on the graph?
Oh, that's a good one. So in this example, we're asked to both minimize and maximize z equals 3x plus 9y with a bunch of constraints.
Okay.
And when we find those corner points of the feasible region, which is bounded, and evaluate z at each point, we find that the minimum value happens at just one point. But the maximum value, which is 180, is achieved at 2 different corner points.
Interesting. So does the dealer have to pick between those 2 points?
Not really. When the objective function has the same optimal value at multiple corner points, it means that any point on that line segment connecting those corners will also give you the same optimal value. So instead of one single best solution, you've got a whole range of equally good options. It actually gives you more flexibility.
Oh, that's cool. It's not always about finding one perfect answer then. There could be multiple paths to the same outcome. What about example 4? That one deals with an unbounded feasible region, right?
Yeah, exactly. In example 4, we're trying to minimize z equals negative 50x plus 20y, and those constraints give us a feasible region that just stretches out forever.
Okay.
So we find a corner point where z has the smallest value out of all the corner points we can find, but because the region is unbounded, we got to do that extra check.
Right, right.
And when we consider the inequality negative 50x plus 20y is less than that smallest corner value, we discover that there are points within the feasible region that actually satisfy it, meaning we can get even smaller values for z.
So even though we found a minimum at a corner, it wasn't the absolute minimum because the region keeps going.
Precisely. In this case, no global minimum actually exists for that objective function over the entire feasible region.
Okay, so that really highlights why that extra step is so crucial when you're dealing with those unbounded regions. And then we've got example 5, which shows us that sometimes you can't even find a solution that works with all constraints, right?
Exactly. In example 5, when you try to graph those constraints, you find that there's no area on the graph that satisfies all of them at the same time. The feasible region is basically empty,
Yeah.
meaning there's no combination of X and Y that fits all the requirements. So no feasible solution and no optimal solution to the problem. This can happen in real life too when the limitations you're dealing with just clash.
It's like trying to fit a square peg in a round hole.
Yeah.
Sometimes those constraints just don't play nice together. Now, the textbook summarizes some general features we've seen across all these examples. What are the key patterns that pop up?
Right. So the big takeaways are that the feasible region in a linear programming problem is always convex, meaning if you pick any 2 points inside the region and draw a straight line between them, every point on that line is also inside the region.
Cool.
And if an optimal solution exists, it's always going to be at one of those corner points, those vertices of the feasible region.
Right.
And like we saw in example 3, we might have multiple optimal solutions if the objective function has the same value at more than one of those corners.
Got it. So those corner points are the key players in all of this.
Yeah.
Now, the textbook also briefly mentions 3 really important types of problems where linear programming is used all the time. Manufacturing problems, diet problems, and transportation problems. It seems like these cover a huge range of real-world applications.
They really do. Manufacturing problems are all about figuring out how much of each product to make to maximize profit given all those constraints on resources like raw materials, labor, and machine time.
Yeah.
Diet problems focus on finding the cheapest combination of foods to meet certain nutritional requirements. And transportation problems deal with figuring out the most efficient and least expensive way to move stuff from different supply locations to different demand locations.
So it's like optimizing logistics on a grand scale.
Exactly.
Cool. And the textbook gives us some examples of how linear programming is actually used to tackle these kinds of problems, right? Can we start with example 6, the diet problem?
Okay, so
Yeah.
in example 6, we've got a dietitian who needs to create a food mix using 2 different types of food.
Okay.
Each food has different amounts of vitamin A and vitamin C, and the dietitian needs to make sure the mix meets the minimum daily requirements for both vitamins while keeping the cost as low as possible.
So it's like a balancing act between nutrition and budget.
Exactly. This usually ends up being a minimization problem, and in this particular example, the feasible region turns out to be unbounded, so we got to be extra careful after finding the minimum value at the corner point to make sure it's truly the global minimum.
Right, we got to do that extra check. Cool. What about example 7? That's an allocation problem, right? Kind of like those manufacturing or resource management scenarios.
Yeah, spot on. This example is about a group of farmers who have a limited amount of land to grow 2 different crops.
Okay.
Each crop brings in a different profit and needs a certain amount of a specific herbicide. The challenge is to figure out how much land to dedicate to each crop to max out their profit, considering both the land and herbicide limitations.
Sounds like a classic farming dilemma.
It is, and this one usually has a bounded feasible region.
Got it. And then example 8 is a more straightforward manufacturing problem.
Yeah, this one's about a company that makes 2 different models of a product. Each model takes a certain number of labor hours for fabrication and a different number of hours for finishing. The company has limited labor hours in both departments. The goal is to figure out how many units of each model to make to get the most profit. And this one also usually has a bounded feasible region.
It's amazing to see how all these different real-world challenges can be tackled using the same mathematical principles. The textbook also mentions exercise 12.2 and miscellaneous examples for those who want to dive deeper and practice applying these concepts to even more problems. Seems like a great resource for anyone who wants to explore further.
It is. Linear programming is such a versatile and powerful tool. It gives us a structured way to make decisions in so many situations where you have a clear goal, but also a bunch of limitations.
It's like having a roadmap to make the smartest choices, even when things are complicated.
Exactly.
Awesome. So as we wrap up this deep dive, what are the absolute key takeaways for our listeners? The things they should remember even if they forget everything else?
Okay, so the big thing to remember is that linear programming is all about finding the best possible outcome, whether it's maximum profit, minimum cost, or something else when you're dealing with limitations or constraints. It involves defining what you want to achieve that objective function, identifying the rules, you got to follow those constraints, understanding the range of all possible solutions, that feasible region, and then zeroing in on those corner points of that possibility space to pinpoint the absolute best solution.
For me, the aha moment is realizing that even those super complex, real-world optimization problems can be broken down into a logical, step-by-step mathematical process.
It's a game changer.
It really is. It's like having a framework for making smarter decisions when things aren't simple. Now, while we focused on the graphical method today, which is perfect for understanding problems with two variables, it's important to know that there are other more advanced techniques out there like the simplex method, which can handle problems with way more variables and constraints.
Yeah, linear programming is a whole field of study.
It is. So this deep dive was just a taste. And here's a little something for you to ponder after this episode. Think about a decision you faced recently where you had different options but also limitations. Maybe planning a project with limited time and resources, or even deciding how to spend your budget. Could you frame that as a linear programming problem, even in a simplified way? What would your objective be? What would your constraints be?
It's a good thought experiment.
It is. It gets you thinking about how these concepts actually apply in everyday life. Thanks for joining us in this deep dive, everyone. We'll catch you next time.